Awesome. Well, I guess let's get started, and I can let people in as they turn up. So great, thanks everyone, and welcome to this rendezvous meetup with Sean. Sean's been busying away generating loads of content, I think, for us to, and examples for us to go through this morning. So I think this is gonna, or this afternoon, this is going to be really nice little session. Hopefully everybody can see my screen, yeah? Yeah. So just want to say that if anybody is not already on the Software Underground Slack, if you could just head over there and quickly sign up. There's a channel on there, RDV Inversion with Sean, and that's where we'll sort of have a bit of discussion during the event and also afterwards. So that's the place to go, especially after the Zoom meeting today, to catch up with Sean and you know, keep talking or asking any questions about the materials he's shared. Right now, though, we've got up to 90 minutes now for a live session here on Zoom with Sean. He's going to take us through a bunch of his inversion notebooks and work. It's an open Zoom, so this isn't webinar mode. So if everybody's just conscious of their mute status as we go, but do put your hand up if questions come up. If it's not a burning question, either drop it in the chat here or on the chat in Slack, and I will try to moderate to make sure we don't miss any questions. But other than that, I'll just let Sean guide us through the content and let him let us know when's a good time for Q&A and discussion and stuff. Great. Well, without further ado, I'll switch over to Sean if you want to start sharing your screen.
Yep. All right.
Cool.
Okay. Thanks, Steve. Hopefully everyone can see my screen now. Yeah, so this, I guess, when the idea of the Subsurface Rendezvous, or whatever the previous name for it was, you know, I'd had an idea, and it was essentially an idea that been popping around in my head, and I've been trying to use in some of my work when I'm inverting data, but it's still kind of, I'd say maybe a half-baked idea, or maybe 3/4, but I thought it would be good to share it with some other people who, you know, may get into it a bit more than you would in a talk. I actually kind of touched on this on a talk I gave a few years ago, and I think it was about a quarter baked at the time, and it just confused everyone, to be honest. And then I just kind of stopped talking about it for a while. So, you know, hopefully with some time, you know, people could just give me some idea, or we can discuss, you know, some of the questions that I lay out at the end. But yeah, so essentially what I'm going to do is just roll through this. This is a curve note article, so it's just things that I've pulled out of Jupyter Notebooks. So the notebooks and kind of the code that runs on them, you could get to from a GitHub repo, which I posted in the Slack as well. But you don't really need that today, but if you want to play along, you can. But yeah, feel free to, you know, download that and install it, and then you can try and reproduce this and see if, you know, what your opinion are of what we're doing. Anyways, so without any further ado, essentially the example I'm going to show is resistivity data. I'm not going to go into it all what resistivity data is aside from this slide here. So essentially what you have is, this is all 2D. So you have a line going along the surface, and you've got current electrodes. So a dipole, current dipole putting current into the ground, and then you measure voltages at other locations. And usually you have a bunch of these laid out, and then you kind of move them along, and you get this pattern, kind of this triangular kind of chevron pattern, and then you get something that looks like a pseudo section. So that's all I'm going to talk about. If you want to know more, there's lots of stuff online. So, and In terms of inversion, I'm also not going to really get too much into inversion. There's links here. One of these is the link to the Simpeg code, which is I'm going to be using, which is an open source inversion code. And then the other link, actually, if I click on it, I can show you, is this geosci.xyz, which again was developed by some people at UBC and has lots of information about inversion and geophysics in general. So if you want to know more about DC resistivity, you could go here, or inversion. But those links are in the curve note document. But I'm going to talk a little bit about inversion because I kind of want to set the stage and set something up, and then I actually don't talk about it for the rest of the thing, but we're kind of going to try and get back to it. So essentially, it's probably, if I zoom in a bit, it might be useful. If I go to full screen and then, whoops. Now I've lost it. If I just going to zoom in a bit. Yeah, it's probably better. Okay. So yeah, so inversion, essentially you've got an objective function which has two parts. There's a data misfit and a model norm, and then there's this trade-off parameter. And your data misfit is essentially just a least squared misfit between your calculated data, your observed data, and then you've got this weighting matrix. And the weighting matrix is a diagonal matrix with the reciprocals of your error estimates. And this is all that I'm really going to be focusing on today is error estimates. Pretty much everything else I'm going to just kind of take as fairly default. I'm not going to play around with them. There's lots of stuff you can do with model norms to affect the results of your inversion. But today, all I really want to talk about is this part, the little sigma i's. So yeah, and so that works in the data misfit part of this objective function. So then we have the model norm, which is, basically trying to recover a model of a certain type. It could be smooth, it could be close to another model, but this, the WM is a weighting matrix, but for our purposes, it's just good to think that it's kind of diagonal-like. It's not strictly a diagonal, but it's, in general, it's diagonal-like. And then we got beta. So how do we minimize this? Common way, and again, I'm oversimplifying and probably mixing and matching things, so don't get too worried about it. But essentially, if this was a nonlinear problem, you could linearize it by saying, the data at some model plus a little model perturbation would be the data at the model plus a Jacobian times that. So you can essentially, now we're solving for the change in the model. So then actually we want to take derivative with respect to, this is where I'm kind of mixing and matching things. Anyways, basically you get an equation that looks like this. You get derivatives, so you got delta M, a whole bunch of matrices, which are essentially the bits of the model norm and the data objective function, and then a similar looking thing on the other side, except you're multiplying by your reference model and your observed and your current data. But what you're really trying to solve for is delta M. And this looks essentially just becomes like a big AX equals B problem. We know A, we know all the bits in there, and we know B, all the bits on this side, on the right-hand side. So we want to solve for X. The details of how you do that, you can't just do an SVD or just an inversion, or sorry, matrix inversion for various reasons of the problem being underdetermined and also very large. But the key is, these two parts are what's going to, what you do to them by choosing beta or setting all the other things are going to affect your delta M value. And so this is all I'm going to talk about it, but there's just three things I want to, to think about is essentially how does your delta M change as beta changes? So essentially your beta generally goes from large to small. So kind of how does that affect each side of this equation? So if this is large, then that's more important than that, and vice versa. And then how are the components of A and B coming to play? Like, I said this is diagonal-like, but what are these things? Well, these are the data kernels, and then these are actually your observed data, and your error estimates are in there as well. So it all kind of plays into how important these WD values are, because it's not just guessing what the noise in your data is, because if you just said, oh, my data is great, it's whatever your error is, 0.01 volt or something, and you just blindly put that in, you're not going to do very well. So, you kind of have to think about how your noise estimates, and I'm going to try and get into that a bit today. So just to start, this is our model. So it's a 2D model. This is actually some data that was collected, I'm not going to say where, but somewhere in the world a few years ago. So, fairly rugged terrain, up and down over a hill. These points are all the electrode locations. So it could be, two parts of a current dipole or a potential dipole, but essentially just moved along the line. Yeah, it was solved with a quad tree mesh, but it's not important. Yeah, and then we get down to our data. So resistivity data is commonly presented as an apparent resistivity, which is a nice way of presenting it. Of course, it makes assumptions when you calculate this value, but so essentially you get a point, and these pseudo depths are just related to essentially your dipole spacing. So as the dipoles get further apart, the plot point kind of goes deeper and plots in between. So these aren't real depths, but it's kind of just a way of visualizing it. So the dipoles were about 50 meters, ends 1 to 6, which just means you went out 6 spacings. In those that cartoon I showed earlier, this one, you'd kind of have 6 of these going out. And actually, as you got out to the larger ones, they were increasing the dipole size, I think, to 100 meters. So it's maybe like an expanding array. I don't know. They have different names for all these things. But the thing to note is that there's actually quite a few data points missing. And these were just rejected during QC. The survey in particular, they're having a lot of trouble getting current into the ground at different times. It's kind of late in the year as well. They're just having trouble in general with the survey. So this kind of represents fairly, a good picture of what you might get in a real case. It's not going to be perfect. There's going to be noisy data that you have to throw out to interpret it, let alone invert it. Yeah, so you'll get a picture like this from your contractor. It's pretty. Maybe you can guess and say, yellow's more resistive, blue's more conductive. But the thing is, the actual data that's going to go into the inversion is your normalized voltages. So it's voltage divided by current. And you can see here that we've got a lot of low voltage values and then a few near surface high voltage. So, very large range and very amplitudes. And this is a histogram of it. So, we've got 2 or 3, maybe 5 outliers up in the high range and then much lower. If we limit the color range, you can see, well, it's limited to 0.1 volts per amp. It's still changing quite a bit. So, this kind of dynamic range that you get in here is all kind of because of the geometric factors that people use to calculate the apparent resistivity, but it doesn't, in reality, the difference between these things is quite small, and it's probably getting close to the noise level of the system. So if you want to invert this data, like I said, you need to assign uncertainties, but you can't just choose, well, I mean, you could choose whatever you want, but there's different ways people do it. Sometimes people choose a percentage of the data. That's a good way of kind of weighing the relative amplitudes. So in IP data, or sorry, DC resistivity data, that's a good way to go, because if you just chose a constant value, you'd be really, really, really focused on the near surface and not so much on the deeper. But choosing 5% is a common starting point, but why not 10? Why not 1? To be honest, if you choose the same percentage for all of them, it's actually just a constant that changes your curve, so it's not actually that important. But then there's more kind of complex things people will do. Sometimes they'll say, okay, 5% for the small n values, but as we go deeper, the percentage is going to get higher just because I think it's noisier. That's fair enough, I guess. But these are all fairly arbitrary things. Yeah, and also you could have 5%, percentage in a floor, but what do you have some constant value, so that if this is small, you don't want 5% of a really small number. Maybe you want 5%, and some floor value. But so these are all questions that I would say in the literature, there's an awful lot of focus on model objective function part, but usually I'd say most papers just kind of say, we chose a percentage and it worked pretty well. But as someone who inverts data a lot for clients, I tend to focus a lot more on this part because I just want to try and get a model that seems to fit the data but fits it in a sensible way. So this is why I've had this kind of question and in the back of my head for a number of years, and why I've tried to come up with this workflow. So we're just going to get to our first inversion. So I did the thing that I didn't know if you wanted to do, just choose 5%. Why not? So these plots, they don't quite fit on the screen all at one go, but pretty close. So they're going to show a whole bunch of these for the inversions. Essentially what it is, the top panels are the data misfit. So it's for all the iterations. I ran these just at 15 for 15 iterations. So data misfit with iteration, so decreasing, increasing model norm. So more and more detail in the model. And then this is just the beta value. And it's actually not that interesting, but I just plot it there basically to show that we're going from a large beta to a small beta value. And all we're doing is at each iteration, just decreasing beta by a factor of 10. And the starting beta value is calculated by the characteristics of the objective function itself, which actually works pretty well. It's just something SimPeg can do automatically, and it works quite nicely. So our first iterations, and these dots will show you, where we are. So I'm going to show a couple results from a few iterations, and then this will be the model, so recovered model. And now we're looking at log conductivity, so the opposite of that apparent resistivity, so conductivity and the log of it. And then this is similar to the data plot, but instead of data, it's the data difference. So it's the normalized data difference. So it's the observed minus the predicted divided by our errors. And then this is just a histogram of it. Okay, I'm not going to explain that for all the other ones. Just now we know.
We had one question, Sean.
Yep.
And that's Dave. I think Dave, you unmute if you like. But Dave's asking, is the data misfit plot weighted or unweighted?
This one? Which plot?
The data misfit plot.
Yeah,
is that right,
that one. Just that, is that curved with the W's in it or not? Or is it just the raw misfits in the data? Or is
no,
it
yeah, that's the whole.
that's
the data norm. So phi d. Yeah, so it's basically phi d plus phi m times beta is so yeah. Okay. So it's the whole thing. Yeah. Okay, so yeah, so first iteration, the amplitudes, it's good to, I changed the color scale on each of these, so we need to keep looking at these, the values in the color bar. But, it's not a great range of values in the model, but it is changing. There's some kind of characteristics. You can see it's quite resistive over here. There's a couple of conductive bits. But in the data difference, we've got some kind of fairly large outliers, which, you can see popping up here, which, it's not bad for the first iteration. It's not, you're not going to be able to fit it all, but as we go down, so if we go to iteration 4, and I chose iteration 4 because the misfit curve kind of seems to, if you look at it close, kind of seems to have these little bends in it, which kind of correlate to jumps in the misfit in the model norm. This point, I was talking to people last night on Slack about, it's kind of a, let's just assume it goes straight. I think that might just be something in the way I'm getting the data out of the code. So don't worry too much about that. But as we go to iteration 4, you can see there's more, kind of refinement of those larger scale features. But we've got this, resistive thing right there, which is right around kind of near that outlier, which, as we pointed out, was one of the major outliers. So it seems to be driving that part of the model, which is fine if that's real. But if it's one electrode that's just, either on some sort of heterogeneous bit of the surface, which happens in resistivity data, or just a bad reading, do you really want to be kind of having that much influence? So if we go to 8, it's again kind of down here, our range of conductivity values is getting quite large. So we've got like 5 orders of magnitude now, whereas here, we're only 3. Yeah, lots of stuff up at the surface. Some people talk about electrode effects. These are kind of I just like to say, we're starting to overfit the data. Like we're getting to the parts where, things down here might be real, but all this stuff up here is you don't want that, and it's probably doing, bad things in general. And you can see, our data difference, we've still got some fairly major outliers, and everything else. I kind of didn't mention this. In a perfect world, like if your noise was really well estimated, you estimated your noise well, and it actually was random, this plot should just look like a bunch of random dots. And this should be nice and Gaussian, and while this is kind of Gaussian, they're still pretty large values. And, you could scale it to make them smaller, but, there's some large tails out there. So it's not, basically what I'm saying is, we're not doing great with our just kind of default guess. And if we let it run to 15 iterations, which I would not suggest you do, yeah, you just get more and more chatter near the surface. And just, sure, this might look kind of Gaussian and that starts to look random, but it's just because you've got really big values and small values. It's not good. So the question is always, what do you do? So you run your inversion, you've made a guess at your noise, but what model should we use? Where should we stop? So a common thing people use is the chi-squared criteria, where, if your noise is estimated properly, your target misfit should be half the number of data. Sometimes it's the number of data, but this data misfit has a half in it. So in our case, that should be around 113. But this point on the curve is actually 615. So, you could just scale those errors wholesale, and maybe make this point 615 or that point 615. But, there's still, do you really want to do that? Because, those models, sorry, I'm scrolling around so much, like even if you chose this one, it's that still doesn't look like like if you scale the errors with a constant, they're still going to be distributed like that. So you're not really, that doesn't look random, which is kind of a thing people like to do when you look at a misfit plot. It should be kind of random-ish. So that's telling you that, you need to do something with your errors, something a little better. So, you could reassign them, manually. Like I said, you could just go in and manually say, oh, that point should have a larger error, that point should have a larger error. I don't like things like that. For one, they're highly subjective. It's not really reproducible. Like I could do it one day and actually come back 2 days later and choose completely, well, not different points, but different values just because of the way I feel. So, and I find those not really very satisfying. So I kind of came up with I call it simple semi-statistical procedure to scale the errors, kind of empirical, I guess. It just seems to work okay. So here's the procedure. So choose an iteration where you kind of think, you're at a point where maybe there's, you wouldn't want to go much further with the way the data is weighted. So get the predicted data from that. Calculate your data difference vector, which was those plots we were showing. So you observed minus predicted scaled to the error. But so that's a vector of all those values. Calculate your mean and standard deviation of those data differences. And then calculate a new error just using this equation. So I'm going to try and explain it a bit why I do it, but absolute value of DD minus the mean, and then divided by the standard deviation plus 1, and then all of that multiplied by the error used before. So if we kind of go step by step through this, if you forget the absolute value and all this bit, what you're doing is if your distribution was Gaussian, you're essentially just shifting it and scaling it to make it zero mean and uniform standard deviation. So you're kind of, you're essentially saying, okay, I want it, maybe it's Gaussian like, I know there's outliers, but I kind of just want to shift it, into the middle. So taking the absolute value, you're basically just kind of mirroring everything into the positive side, because if you're multiplying it, using it as a scaling factor, you don't really want negatives. You just want all positives. So then it'll be kind of mirrored around 0. But because I'm scaling the previous errors, I want to add 1. So I add 1 so that, the points that were kind of at the center of that scaled distribution or shifted distribution those are the points I'm kind of happy with. Things are going well there. So I want the error to stay the same. So, they would be shifted to 0, add 1, multiply by error. But if it was one of the outliers, it gets contracted a little bit and shifted around, but that'll be a non-zero number, and that'll be added to that and then scaled. So it's tough to describe. I didn't really explain it very well here, but this is basically I probably should have plotted different things, but this was our original error estimates. So I've decided iteration 1 is where I want to stop. I'll kind of just use that because we've already got these massive outliers here even then. So I calculated the mean. So it's not really Gaussian, but it's, the bulk of the stuff kind of lies between the standard deviation plus and minus. So that's fine. And then by applying that equation, I get these rescaled estimates, error estimates. So you can see the bulk of them are still kind of near 0, but we're getting, kind of larger values, so 0.3 instead of 0.125. So we've increased our error estimates for some of those outliers. So rerun the inversion. So I just restarted the inversion from the beginning. Just why not? So options to kind of continue on if you wanted to, but I found it easy just to do it over again with the new errors. So here we are with iteration 1, the model, that looks similar, but it's still pretty nice and smooth. It's not quite this, those outliers aren't as prominent anymore. This is our distribution of differences. We don't have those kind of that tail that was out here. They're not Gaussian, but they're a little more random. There's still some patterns, and then if we carry on to iteration 3, we're starting to get that kind of bad guys back, and you can see them down there, but the rest of them kind of look a little Gaussian, and that was where that's where we kind of had that low resistivity or low conductivity, so high resistivity bit before that I was a little worried about, but it's kind of gone, and we're seeing some more detail. So why not rescale again? So we'll do the same thing, basically perform the same rescaling, because I don't really like that. So we do the same thing again, rerun the inversion. One thing you notice kind of first off is that this curve actually starting to look, it's not, doesn't kind of have that kind of 3 stages of thing. It's kind of just more of a smooth descent. This isn't as bumpy. Our iteration 1 looks similar. Data differences kind of look okay. We can get all down to iteration 5. That's actually quite a nice distribution of errors, and they're actually all quite small. So yeah, I think it seems to be working pretty well. And if I'm just going to try and, this is just comparing from the 3 inversions at iteration 5. So each iteration, they're all plotted on the same color scale. My scroll wheel doesn't want to behave, but we can kind of see that, this has quite a large dynamic range. So this is, quite low and high conductivity. This one's a bit smoother, but, it doesn't have these kind of outlier bits and, that kind of near surface chatter that I was talking about that, is, it's in there because there's noisy data, but it's not what you're interested in. These guys aren't doing a survey to try and find stuff there. They're looking for mineral deposits that are, hundreds of meters down. So this is kind of a distraction, and you want to minimize that. So if we look at the data difference plots, kind of get a similar thing at iteration 5. These are all plotted on the same scale, so plus or minus 10. So with our original errors, kind of very large, outliers, well, and not the massive outliers anymore, they're kind of off here, but as we go down with rescaling and rescaling, of course, the color scale hides a lot of outlier sins, but with the histogram, you can see it's really tightening things up. So yeah, so that's basically the idea, is instead of just manually choosing your errors, kind of use this little equation and then either restart your inversion and rerun it with new errors, or you could probably carry on. So I don't know how long that's been. Half an hour, that's not too bad. So yeah, so before we dive in, I didn't say this beforehand. Yeah, anyone could have interrupted before, but I always like when I give a talk to finish off. Usually, I have the last slide with questions that I'd want to ask myself because I want to preempt other people asking me the questions. So the questions, I'm showing iteration 5 for whatever reason as a good place to stop. But is that the best place? How would you know where the best place is to stop? I don't know. Again, it's kind of, it becomes subjective. You can use some of these, L curve criterion. I haven't done that with, if I scroll back up. So this is, if you plot data misfit versus model norm, you can get the Tikhonov curve and get a corner. This curve is a little wonky. It might not be a great L. It probably will have an okay L. It'll definitely be better than the one from up here with all these jumps and things. Yeah, so that's an open question. Again, it's subjective, but yeah, and even choosing what iteration you want to rescale at, I've kind of used it as, looking at little breaks in the curves or just where there seems to be some data. Again, that's fairly subjective. Maybe you want to do it at every iteration. Like how many times is good? I don't know. Could you, if you did it every iteration, what happens? I don't know. The main reason for that is I mainly use this for magnetics inversions, and I run my magnetics inversions using Voxy, which is a proprietary piece of software. So it's a lot of running, exporting, getting stuff in, getting stuff out that takes a lot of time and a lot of hassle. So with magnetics, I usually just do it at the first iteration and kind of, it seems to work pretty well. IP, I usually use the DCIP2D code, which is similar to this, but it gives you a lot more flexibility in terms of output. So I typically usually only do 1 or 2 rescalings, but yeah, how you do that is kind of an open question as well. So
do you want to, I don't know, Sean, do you want to keep going? Do you want to invite some discussion around those first 2, or?
Yeah, sure. I mean, or I'll just say all the questions and then people can chime in wherever they want. Yeah, so then the more general questions, which Steve put up on the site, which I'm quite interested in, is, does this make sense theoretically? I'm not a statistician. I read a paper about iteratively reweighted least squares years ago, and this kind of looks a bit like that. But whenever I read those papers, it very quickly gets into lots of stats and proofs that I don't understand. So, I mean, I imagine that this isn't a new thing. I've probably reinvented or partially reinvented the wheel or just used something, but I'd be interested to hear from people about that, who know about that sort of stuff. And yeah, and if anyone can recommend a smarter way to achieve the same goal, that would be great. And, I'm always wondering whether it's worth the extra effort because, particularly when using, I mean, with the SIMPEG codes, it's pretty easy because you can stop things and start things and you have control over the input and output. But if you're kind of wrestling some proprietary code to make, bend it to your will, which I'm doing a lot of the time, it is a lot of effort, and I think it's worth it. But yeah, then the last question was, I forgot to go back to the matrix equation because that's another thing I think about is just, and I think that kind of gets into the theory of it, like just, how with a large beta, how important those, that your weights are and, yeah, anyways, so yeah, if people have any questions or want to comment, go for it. Because I don't have answers to these questions.
Yeah, I posted the link to IRLS. I think it's something I've used a lot, and not that I believe it, I know what the norm is, but because it generally produces a more robust procedure and you can philosophically think of it as, every iteration I'm going to redesign my W matrix based on what the current residual is. So I have some function that turns my current residual into an estimate of a new weight number. And I've used that on things like statics over the years, and it doesn't do anything other than do what you ask for. So I was very excited once when I first used it that I came out with did L1 and I came out with exponential residual histogram. But, you know, and if you do L2, it comes out with a mostly a Gaussian residual. You know, it just does what you ask for. So rather than saying, I know what the noise is, you're sort of abstracting up one level and say, you know, I know what the form of the noise is. It's not Gaussian, it's L1. And then it comes up with a procedure on how to design that reweighting function that's sort of related to the norm you chose.
The thing that excites me about Sean's method over the RLS, though, is that if you have, you know, data that belongs to very like different spaces, for instance, like the dipole example, right? If you have very long offsets, they're very different data than the short offsets. Or if you're like, you know, doing like frequency domain, frequency blocks are very different from each other, you know, and then
if you start to regard IRLS as a way of, you know, iteratively estimating your noise levels, then you start to like do smart stuff like you were saying and say, well, do I know something about the structure of the noise because I made this experiment, and how can I embed that in this noise estimates? Because, you know, IRLS with raw L1 knows nothing about your experiment, whereas you, having designed the experiment, you know something about what you expect to be noisier. So I think IRLS to me is one example of a way of iteratively coming up with new noise estimates. But, you know, in real world cases, you often know more than that and should sort of try and put that in somehow into the procedure.
And I guess that's a question for Sean and you, Dave. So right now, Sean always restarts, right? He restarts from the top. And I think it's in my opinion, it's probably a good idea because, you know, you can have such a large change in, you know, in the difference between the two functions, right? Every time you change something in one part, beta needs to be readjusted or somewhere level, right? How does it work with the RLS? Do you find that your iterations are jumping enough between the updates, or yeah, what's your take on this, Dave or Sean?
Traditional RLS is for a linear problem, so it's a bit slightly different than this non-linear problem.
And I guess at the beginning,
on linear problems, I have generally kept going. I've generally not moved too far down the curve before so, you know, if you were doing 100 iterations, my rule of thumb was 10 IRLS reweights of 20 iterations. So like pay double the money, but do it in 10 chunks is not a bad 10 reweights but in a linear problem. But in a non-linear problem, you have that beta parameter sticking in there, which is kind of doing a related thing. It's sort of saying, how much do I believe my data versus how much do I believe the model, and that sort of belief is something that is changing, and, you know, as non-linear iterations go. So, you know, I like to, you know, sort of say, think Bayesian and then do whatever seems necessary to get the job done, you know. Understand what it means in a Bayesian sense. In a Bayesian sense, you're saying early in the thing, I don't believe, you know, when beta is big, I can't remember which one beta's on in your case. I believe the data a lot, and then towards the end, I'm going to be more cautious about updating the model. Might be the other way around. I don't know which way it is. So
yeah, I mean, the thing that I've just back to Dom's comment about different types of data. Yeah, with mag, it's actually kind of interesting because you know, I think magnetics is one of those ones where, you know, percentage in a floor is, you know, pretty common. But if you when you choose those two values, so you choose, like in this example, I just chose a percentage. So, you know, you can rescale that and it kind of changes, and that's fine. And if you chose a constant, you can move that around. But if you chose by having both of them kind of defined by the user, you're basically making the relative importance fixed. So just doing a scaling, kind of a linear scaling of those errors really doesn't help you very much. Like I said, like if you just did a percentage in a floor and then instead of reweighting, you just said, oh, I'm just going to scale them to make, you know, phi d be the number of data, but then your noise floor might be too high or too low. So I found with the mag, it's actually, and I didn't have an example of that, but because in magnetics, you know, probably the majority of your anomalies, you know, responses are about the same amplitude. So the weighting, the data weighting isn't quite as important from a numeric sense, I think, as this resistivity problem. So what I found is I would start with a constant value, and then through this rescaling process, and even just doing it once at iteration 1, what you come up with actually looks very close to, if you chose a percentage and a floor. Like I've kind of compared them just to see if I'm doing it, except over places where there's something strange going on in the data, there's usually, a higher error estimate. So I guess that's kind of one of my empirical feelings, that it's kind of doing a good job, in the sense that, and maybe that's why I feel it's worth the extra effort, is because, just, it looks a lot like an error, like a percentage and a floor error. I should have got a mag example to show you, but I wanted people to be able to play along with it. But yeah, the IP or the resistivity it's difficult, because like Dom said, that, it looks like a map, but this data point is very, very different from these deep data points. And yeah, and you can get, things can be affected by just the surface conditions here, that, it can kind of affect a whole load of dipoles. And yeah, so it's quite useful. But
that depth is a proxy for offset, is it?
yeah, I mean, for the plotting. Yeah, just for the plotting.
What does a single bad station look like on? It looks like a line. Like
yeah, it could. Yeah, if there was something really wrong, like, or just something weird here, yeah, it could be a stripe. I mean, if we go back, like some of these, you can kind of see them. There's one of the plots that had nice stripes in it. Anyways, now I've lost it.
Easier to see when it's filled in, right? Not just the points. Yeah.
Yeah. Well, like that, you could see that
yeah.
kind of angle. That's probably something going on there with maybe something on the surface. So.
Or it could just be a surface conductor too, right? That's the hard thing, is that we don't know. We don't know what's noise, what's not noise.
Yeah. So, but yeah, but
I guess that's what IRLS could tell you, is if the philosophy at least, if it looks like that, if the error looks that shape and it's completely inconsistent with all the other guys, then I'm more likely to believe that this whole station is bad. And
yeah,
that's, what I'm thinking, that's the opportunity to put something about the geometry of your experiment, more than just, these aren't independent data points. It shouldn't really be a diagonal thing. So, if you know that a bad station would have a pattern, can you design your RLS, your weights updates to in a sense, look for the pattern of what a bad station would look like, or something like that.
Yeah, I mean, that's kind of also what I was, this is something I was actually interested in for this discussion, which I didn't, when I first talked to Steve about this, I had this massive plan that was going to probably take 3 days to present and months for me to prepare. So it's probably good he talked me out of that to do something slightly more simple. But when I think about this in my head and try and figure out what's going on, I often kind of think about this equation and what's happening. So like so in the case of, let's take an example where our reference model is either a half space or it's zero. So in our case, it's a half space. So this term, for the first iteration or the start of the problem, this term's basically zero because the derivative of half space is zero. So that's gone. Let's just say the model was zero as well. So that's gone. So it's really, the right-hand side is just this, your observed data kind of multiplied by some of the weights and then by your sensitivity matrix or transpose. So, which I think I've read somewhere people call that back projected data. I don't know if that's true or not. I thought that was kind of interesting though. But then over here, we've got your beta is going to be very large. So, this term is, essentially not super important, or is less important. But so as beta goes smaller, and again, this would be like in terms, if beta was just a little bit smaller without changing anything else, so big but not so big that, it totally outweighs this, you're essentially, and this is kind of like ridge regression type things, this is kind of diagonal like, so you're basically adding a whole bunch of stuff to the diagonal of this matrix. And so when this is really big, you're just basically getting a diagonal matrix. So it's going to be smooth or kind of just nothing. And then slowly, you're kind of adding information from your data kernels, from your sensitivity matrix, weighted by your error estimates. So this is where I think kind of the idea of your error estimates, not just, being noise, but they're kind of the relative importance of different parts of your data comes in. Because the way I think about it is that, like, even when beta is really large, and we're not really that confident about this part, you're still getting something like, iteration 0. I mean, that actually looks like the data. I mean, the amplitudes are probably way off and everything, but that pattern of like resistive, more conductive, resistive, is, it's kind of like this. The colors are reversed, of course, here because it's resistive, but there's resistivity, conductive. So even with like this very, very large first iteration beta, where we're really supposedly ignoring all of our data constraints, we're getting a pretty nice pattern. And that was kind of where I thought, like, well, if everything is going to plan, like, say, if you're using synthetic data, so none of these weird little things, you'd probably just progress quite, in the same descent direction, basically, until you converged on your answer. Maybe at the end, you might weave around a little bit. But, this kind of general structure of your model is right. So it's as you get, move on and get these things, it's either that these things are parts of your data that are interesting, or they're things that can't be modeled by the physics, like maybe they're 3D effects, or they're just noise that is some weird heterogeneity that, you can't capture. And so that was kind of my reason for thinking, like, well, it's good to stop and say, okay, well, this is a good first order representation. So let's stop here, calculate what our errors are, and then everything that doesn't really agree with that, we're not interested. So what I really, I mean, I just like kind of looking at problems in a way. So what I really wanted to do is come up with a toy problem that we could actually investigate this, because of course this problem is like all sparse matrices, and you never actually form these matrices, and they're all solved with solvers that I don't understand. So, because I kind of I like that idea of, as you kind of go down beta, at a certain point, you're getting to see the bits that they don't agree with something. And again, it becomes subjective, but I was trying to figure out, maybe there's a way, to statistically say, okay, well, this is a point, and maybe it's where these kind of kinks in this curve are. That's why I picked them, because I think something's going on there. Like the character from that model to that model, it gets a lot more noisy. And the bits where stuff are being added is the bits of, like I said, the bits of the model we're not interested in. So you just don't want this. And I think you see one sees these types of things quite often in presentations or data that you get given by someone else, and it's quite frustrating. So it would be nice to be able to develop some sort of methodology that wasn't subjective, so that it could be packaged into something that could be used by people, because more and more of these inversions are becoming black boxes, even though they aren't black boxes and shouldn't be used that way, but they're being marketed that way to people, and they're being used that way. So that's kind of not only to make my life easier, not have to mess around with this stuff, but make my life easier so people aren't overfitting data and kind of giving inversions bad name. So
I think one interesting question on that is, you've just said something that's very common, which is, I don't like what the result looked like.
It's true.
And so the question is, well, if you don't like it when it looks like that, why did you tell it to do that? Because you did tell it to do that.
Yeah, well,
so
I mean,
the question is, so my question is, is that more on the model side of saying, I don't believe this result because it doesn't fit my view of the model, but somehow I haven't expressed what I don't like in my model, covariance part. So it might be more on your M side than your D side, that you're missing something, or that somehow it's the balance between the two. You haven't told it, I don't want like little tiny single point defects in the model. So it's like, hey, look, I can fit the data really well with this little point defect.
Yeah, well, I mean, I guess in reality I have, because it's basically it's supposed to be penalizing. It's supposed to be making as smooth a model as possible. I mean, I haven't expressly said like this layer here, but you know what I haven't done is told it to stop. You know, it's just going and going and going and fitting the data. That's, you know, it should stop before that. So that's kind of what I'm saying. It's like, as you overfit the data, in my opinion, you're overfitting the data, because it's you know, these little things here are just, you know, changing small parts of the data misfit that aren't important. Yeah, no, I take your point, but
you can always do mesh engineering. I would always make those near surface ones really wide instead of having little points. So it would force a regularization, and you know, you have tiny little mesh blocks right at the surface. And so if you make them, you know, whether that's bad practice or lying to your clients or however you want to phrase it, but that's something that I would do, you know, with the first 1 or 2 cells, because already the value of those cells, you know, if it was a massive hunk of gold on the surface, I think that you wouldn't need geophysics to find it, or the inverse. If it was a massive karst cave, you also at the surface hole, you wouldn't, you know, use geophysics to find it. So I've definitely played some tricks like that. And then my other question is, I really like this. I've done similar work in, you know, frequency domain geophysics. But if you just put the image in a report to a client, is there a difference? You know, if you don't report the noises, if you don't report the residuals, if all you're doing is subsurface image drill here, whether you do this process or not, do you think that your final result changes much?
yeah, I mean, that kind of goes to the is it worth it question, which I think is a valid one. I don't know. I've made the conscious decision that I care about it. So I now make a whole bunch of plots that I give to my clients who probably don't want them. I give them data residual plots, and I explain to them what I did, and most of them don't care. They still just want the image, and they want the, you know, ISO shell of where something is. But yeah, I don't know. I mean,
no, I 100% agree. There's no way you understand less about your data. You know, whether you've done this at iteration 5 or iteration 1 or iteration 10, you're going to understand your data more. You're going to understand the problem more. But I've definitely also worked with clients that just wants you to draw a circle with an X.
I think I gave another talk kind of on similar things, and one of the answers I gave for why it's worth it is that more and more people are taking these, like, you know, sure, if you're just drawing a circle, you know, any one of these, you know, you're probably going to see that, you know, the amplitude's, excuse me, bigger there, but you know, that's still an anomaly. That's kind of slightly different. But I think more and more people are, you know, wanting to take these models and do other things with them, you know, either put them into a machine learning algorithm. You're also just giving them to someone and they just take them and do something. So someone might say, oh, you did a 2D IP inversion on your project. Can I have that model? And they'll just get sent the model. They won't even get sent the report. So the report might say, actually ignore the top, you know, 3 cells on everything because it's garbage, but they won't get that report. So, you know, I've really, over the past couple of years, become quite, I don't know, maybe to myself, quite strict about this type of stuff. But yeah, no, I don't know whether a lot of people care.
There was one question from Alex in the chat where he was asking and pipe up, Alex, if you'd like to ask it yourself, but it was asking about, could they predict the issue with currents going into the ground, i.e. by knowing that there's clay or groundwater there? I think that was your question, Alex. Did I get that right?
I mean,
That is right, yes.
So essentially, maybe put the electrode somewhere else if the ground is, not great. Yeah, I mean,
Well, I don't know if you know the ground quality
yeah. Well, I mean, the guys.
condition somehow.
I mean, sometimes they're out there and they're just it's just really rocky or clay. Yeah, I mean, it's a problem. The difficulty is, I mean, with 2D surveys, you want to do it in a profile along a line. They're hired to do that. Their boss tells them to do it every 200 meters, and they've got a little bit of leeway this way or that way to find a good place. But so yeah, no, it's just and it's really site specific. I mean, this is a project where, if I remember correctly, on one side of this, maybe this hill here, it was there was just a massive change in geology. Like it was limestone over here and something else. I think it was a porphyry target. So there's, whatever the kind of country rock, and then the intrusive maybe, I can't remember the details, but you look at data from places like Arizona where it's really, really conductive, and it's the opposite. It's just, here the current's probably just going away. There, the current is, going in a different place. So yeah, it's a difficult, it's an idiosyncrasy of this type of survey for sure. And how to overcome that, I usually just leave it to the field people, because it's beyond me. I just try and give them as much support as I can. Tell them I know they're working hard. Good job.
So there's some more comments from Alex in the Slack. He said suggests stress testing against errors which are not Gaussian. And I like the way that the errors seem to get closer to the optimal for L2 optimization. I don't know.
Yeah, I mean other norms. That's another thing. I mean, like I mentioned before, there's a lot of a lot of people write papers about different types of norms for the model, and I think there is a bit like IRLS. I mean, I do remember reading a paper, and I keep meaning to find it, or maybe I did find it and I couldn't understand it, but I think I've only ever seen one or two, at least in terms of the kind of type of geophysical inversion I'm used to reading about. But yeah, there's no reason you couldn't have a different type of norm that could, look at different, actually, there was a talk at the SEG a couple of years ago by Alan Jones about that, using not a chi-squared norm, but I can't remember the name of it, some other one that actually looked at spatial distribution of errors, which was quite interesting, if you had like a plan map type thing. But yeah, no, it's a good idea. Again, this kind of came about from the way of someone who uses codes who doesn't write them. So you're kind of stuck in a way with what you've got. So that's kind of how I approach this problem. It's not like I was able to come up with a new norm to apply to this inverse problem. I'm kind of dealing with closed codes and just how to make the best out of them.
Cool. There was a question from Thomas: why DCIP over SimPeg?
Because I could buy that code and use it without having to learn how to use SimPeg. As a consultant, I've wanted to use SimPeg for 5 years, whenever. 2016, I think, was maybe one of the first times I heard about it. And it's always been on my to-do list of, I got to get into it. And in the last month and a half, I was telling Steve, I've actually done a fair bit finally diving into the code, and it's amazing. It's hugely powerful, but there's a learning curve, and that learning curve is also compounded with my lack of proficiency with Python and just plotting things up. So yeah, DCIP 2D from UBC, it costs money, but my clients pay me money to invert their data, so that's why I used it. But no, if you have the know-how, I'd say use SimPeg. Go for it.
Cool. I think Adaraloye had a question as well. I don't know if you want to comment around dipoles with deeper penetrating power. And the question is that something you want to still relevant and you want to ask about? Adaraloye, if I'm pronouncing your name correctly, sorry.
Well, yeah, I mean, definitely the longer dipoles, are in theory, well, they do see deeper. So yeah, that's kind of goes back to what we were talking about of the fact that, it's not, this data point here isn't really the same as this point here because it's, it's currents flowing, all through the near surface. So yeah, the currents that are input are also changed. That's why it's generally the normalized voltage that's put in. So actually, when I look back at this data and what I did when I ran it, which was probably 4 or 5 years ago, I actually estimated the noise based on the measured voltages and then scaled those, normalized those to the current. So actually there was just, the error estimates were all over the place. And so I used that as a floor. And then I think I added a percentage. I did it before I'd come up with this procedure. It worked okay, I think, but yeah, no, it's a good, it's a strange one because I find DCIP data just, I find it difficult to wrap my head around sometimes. And IP is even worse because then there's like decaying voltages and the noise has a lot to do with, the current that's getting down. So these are thrown out. I think at the time I was throwing all of the data out if there was bad IP. I just threw the resistivity out too. Probably wouldn't do that now, maybe, but it's a problematic data set.
Dave, do you want to ask your question there on the plots?
Yeah, I was just wondering, I couldn't remember if you'd shown us what the weights looked like at the end and whether they were diagnostic of anything. So whether you could see a bad station, for instance, from the weights, and whether that might be a product of this, some sort of QC measure that could go back to the operation.
No, I didn't plot the weights. You're right, the errors themselves. No, I could. If I was really
Mostly since
brave,
you're saying that you're getting back the percent at the end, it would be interesting to see what kind of percent you're getting at the end.
Would it be a field QC thing that says like bad station should like jump out at you? Like if everything associated with this station has a high error, then that's probably something you could, if you had the ability to look at it and fix it, it's something you could do. But maybe if you were doing it in real time, but
yeah, I mean that's it. Definitely, I would say for this type of data, you get something, yeah, with a couple of points that are really, that have very large, and sometimes they have a pattern associated with them, but sometimes they don't. It's much different. Again, I talk about mag data a lot. Magnetics, it's usually, kind of more on, higher amplitude anomalies will have, just because it's slightly more difficult to fit sometimes, so you'll have larger errors around them, which is kind of more of a, it's like a numerical, it's not a, I don't know what, it's not an error in the data, it's just, I guess, the physics in the, you're struggling to kind of fit these things. So with the smooth model. So yeah, IP and DCIP are slightly different. So yeah, I think the thing is, in terms of a QC tool, I mean, just even QCing the data, you can look at the data and, I mean, I think I showed, the very first plot, just the amplitudes. I mean, you're going to know which ones there are. It's like, it's these ones. And those are the ones I kept talking about the whole time. And, typically, they'll take multiple readings. And as long as, I think the field procedures are usually, if you can do 3 readings and get the same thing, just keep going. And whenever I've asked, field crews before, like say, oh yeah, station, whatever, looked a little weird. And they just go, oh yeah, man, that was brutal. We spent 3 hours trying to dig a pit to get some sort of contact with the ground. And like we poured 30 gallons of salt water on our rods and, still we couldn't get any current in the ground. So at that point, I'm saying, okay, you tried. I mean, that's, that's all we can do.
Sean, you raise a good point, and I think we haven't talked about this, right? Is that the noise is just not the data noise, it's also a numerical noise. How well our mesh can basically replicate the physics, right? So that's usually why the near surface are much harder, because the dipoles, the accuracy basically on our modeling is very poor. So I think it would be really interesting to rerun exactly what you did, but breaking the mesh down in factor 2 and see where the noise is actually, like the noise is actually happening, because that's something we're kind of pushing under the rug, how well we're numerically simulating things, right?
Yeah. Yeah, it's interesting. I mean, it's another one where like DCIP data or frequency domain EM data is, or any EM data for that matter, it's much different than potential fields. Like, I mean, I gave a talk a few years ago about, that idea of what you should really think about what you put into your inversion algorithm, because if your model, if your code can't reproduce it, it's gonna look like noise. It's gonna cause you problems. And with potential fields, you can do a lot of filtering beforehand and basically take things out of the data or suppress them that you can't model. But you can't do that with IP data. I mean, I guess you could throw away all the small dipoles. I mean, I've heard people say things like they'll run an inversion initially just with the large dipoles just to kind of get a background, and then, kind of do an iterative thing like that, which is fine. I mean, because your depth is kind of coming from a geometric thing. But frequency domain EM, I guess you could do the same thing, but you're still struggling with the problem is that, your long offsets aren't just sensing deep, and your low frequencies aren't just sensing deep. They're going through the entire Earth. So it's a tough one with these kind of EM and electrical methods. So, and yeah, and going super fine, I always wonder about that, because I mean, again, I've only really started looking at IP data in the last few years, and I can remember seeing talks by people, and they'd always talk about these electrode effects in inversions, which I just always think are it's all the cells near the electrodes just struggling with whatever the local heterogeneities are. And I wonder if you made the mesh really, really, really fine, like, are you just gonna end up with a bunch of little blobs around the electrodes and still
You
gonna have
regularize that against it, right? I mean,
yeah, I guess so. I don't know. I kind of like a simple kind of like a simple solution. I don't like having to fiddle around. I guess what I'm trying to see is if I could come up with a solution that some person who doesn't understand the code very well can kind of do on a regular basis, then I like that solution.
it's a good. I love what you're doing. We'll try it for sure. Absolutely. I'm just saying that, yeah.
It's definitely
noise is more complicated than data.
Oh,
noise,
absolutely,
right?
absolutely, 100%.
No, that goes all the way back to Tarantola. Like, he's specifically split into modeling. It's really the estimate of the error in the residual.
Yes.
So it's split into modeling error and data error, data noise, if you like. And he told you how to add them. Inverse variance is add. So, and I think that's kind of interesting with the percent plus floor thing, because I kind of feel like the percent, if modeling noise is more likely to be a percent.
Yeah, absolutely.
Whereas data noise is more likely to be a floor. So I don't know whether that tells you anything about which one should be bigger or smaller. I have no clue, but
yeah, no,
having
definitely.
both parts in there is, especially if you're doing 2D on 3D problems,
Yeah.
My question is the modeling error in 3D worse? Why do you scale bigger offsets? Is it because the modeling error in 3D is bigger at bigger offsets? Have we come up with procedures that are really work but not really understood fully why they work? Are they really in the physics or somehow? Or the simplified difference between the simplified physics and the true physics?
Yeah, no, I mean, and that's a whole other thing. I mean, getting into 2D and 3D, like this, DC resistivity surveys in particular, I mean, you're essentially, you're collecting, it is 3D data because the source, currents can flow everywhere, and they do, but you're really just, kind of putting everything down a line. So you assume the world's 2D, but, you could throw this data into a 3D inversion if you wanted to, and even with multiple lines, generally you're not reading across the lines. And yeah, I think people are moving away, they're moving to, different array designs, which, actually are truly 3D, and things get quite complex quite quickly. But these kind of old diehard methods really, they're hard to break people's habits in exploration geophysics. Someone wants an IP survey in northern BC. This is the kind of survey they want. You can try and sell them a nice 3D survey, but it's going to be tough. So that's a whole other issue, I guess. Maybe that's the real world part of it, is that a lot of the time just get data and I don't have any say in anything.
So Eric Root shared a paper in the Slack channel. I don't know if you can see that, Sean. And that's by nonlinear inversion units in general measures of misfit and model structure.
Yeah.
And he's just asking if that's a paper you'd seen or you'd been inspired by.
I think that might be the one that I was saying that I've had a vague memory. Is it by Rob Ellis?
No, it's by Colin.
Colin. Yeah, it's by Colin.
And Doug
yeah.
Oldenburg.
Yes, that would be it. Because I was at my master's, Colin and Doug. Well, Doug was my supervisor and Colin was still at UBC.
I think Doug's on the call, is he?
Yeah.
Potentially. I think so.
Yeah, so I mean, this is the idea of just not using just L2 norms for everything, but, mixing and matching. So yeah, definitely. And this goes to the kind of the IRLS stuff that we've been discussing. But again, I mean, these are, you need to have a code to run it. And I'm not saying, they don't exist or one couldn't program it, but I don't have it. So, but yes. Thanks for the reminder.
In terms of the models and stuff you've been running, what sort of computation time are you talking about for those inversions?
Oh,
and I guess how does that compare with
minutes?
With running it? Minutes.
Yeah, I mean, these are small. I mean, oh no, how do I get back to where I was? What was
a different time?
Panicking. Yeah, no, a minute. I mean, yeah, these are minutes. Not long at all. I mean, and it's it's not a big survey line, 2 kilometers almost. That's a typical thing you'd find. I think the DCIP code runs pretty fast as well. So yeah. And I think the DCIP one runs much faster, but it's all parallelized, and I'm just running this kind of just on one core or with no kind of optimization. So yeah, no, it's definitely comparable and doable, with a regular computer. So yeah, I don't really have, what were the other questions that I had? Anyone else have any comments? Thanks for that paper, though. I've forgotten that Colin and Doug had written that one. I know I've seen it before. I have to say that. Yes, I did reinvent something. That's good. Colin obviously came up with a smarter way to do it. That's good. Yeah, I don't know. Yeah, I mean, stopping inversions is just, that's a whole other, that kind of ties into noise estimates as well, because a lot of times you're stopping because you'll see this, going back to the comment, I can't remember who it was, who said, just put the thing in the report. And you read this in reports all the time, we did an inversion and converged to an RMS level of 1 or 5%, and that's good, but yeah, if your errors are just kind of randomly assigned, those numbers don't mean anything. So I'm always interested in the idea of when you stop an inversion. There are things like, the L curve I mentioned. Another one is generalized cross-validation, which kind of was popular 20 odd years ago when I was doing my master's. I put that into some code I wrote. It's used primarily for splines. It works well with lots of data, and our problems a lot of the time is we don't have a lot of data, or the data isn't probably whatever that misfit kind of topology isn't good enough to find a minimum for a GCV thing. I don't know. Dom, are people still playing around with GCV at all at UBC or SimPeg? I know you're not at UBC anymore, but or anyone else know of codes that are using things like that, like statistical kind of methods?
Now, the last one I saw, it was the CIP2D, right? And I know that Nick loves it. So
does he? Oh, okay.
Someone should work on it.
Yeah, it's an interesting idea. I don't know if people don't know what it is. I'm not going to describe it well, but I think in the paper they describe it as it's a leaving one out procedure. So essentially, you kind of I think you propose a model, and then you perturb it, but you progressively just leave one data point out, and then you leave a different one out. So you're trying to reject outliers, but it does it not. You don't have to iterate through it. It builds a function, and then you find the minimum of this generalized cross-validation function is kind of where you think you should go, and it's kind of a way of choosing the beta value for a given iteration. When I did it, I was using it on frequency domain EM data, and it had the tendency to overfit things. So if this was, there's lots of different ways to choose beta as you go, and one way would be to use this GCV. Like you linearize the problem and say, okay, choose a beta value that seems best. And early on, it seemed to just overfit data and add a lot of structure that wasn't nice. So maybe there was I think people proposed, I think Colin actually might have done a paper, maybe doing like a hybrid thing where early on you use a cooling schedule, and then later on, when you're close to the solution you use the GCV. But then you have the same problem of how do you know when you're close? So I guess that's my difficulty is, I read all these papers, and I don't say that dismissively, because the research is amazing and it's hugely important, and stuff like this is great, but it's always the next step of, as a researcher, you're doing research, like you're not using it that many times a day, or so it's the question of, how many iterations should it go? Is it always the same? Does it depend on the data? And the answer is probably yes, it always depends. But so those are the kind of problems that I like to focus on, because the fundamental research is a bit beyond me.
Cool.
I put in a link to a paper by Alberto Malinverno, who's someone who's thought a lot about these things as well.
Okay, cool.
How to make models simple, or how to estimate the miracle parameters, this sort of hierarchical Bayes thing of, making the beta effectively a hyperparameter of the problem, and saying, what's the best fitting combination of data weight and model weight that makes this most likely to be the right solution? Is sort of it gets pretty mathematical as well, but they have a nice simple example of doing sort of 1D well log inversion.
Okay.
For this sort of thing.
Yeah, that's a whole, the whole Bayesian thing is, it's just something I haven't been exposed to, and again, I when I come across papers and read about it, I'm fascinated and always want to kind of try and dive in, but I haven't done it. So that might, because it makes sense. Like, yeah, when, like you say, when you start actually trying to define a shape to a probability or something, it's the smart way to go, I think. So maybe there's something there, or maybe, like you say, it's already been done. So yeah, I'll check that out. That's cool. Thanks.
Cool. Well, we're getting close to time. Was there any last comments or questions? No.
Yeah, but I'll just make a last comment. So yeah, like all the data is on there. The results from these inversions are there as well. There's some kind of pretty kludgy functions in a script to pull data out and plot it. And then I wrote a lot of it actually this morning, so it's pretty messy, but you should be able to reproduce these. And I actually ran a whole bunch of other inversions with different errors. My grand plan was going to be to look at all of them, but clearly this was enough. But like I did some with a percent and a floor. I did some with different percentages. So yeah, it's something I might, to try and carry this conversation further. I'll take a stab at actually looking at some of them maybe, and actually, just seeing how the rescaling works, or maybe, yeah. But yeah, if you want to have a play around. And the inversion code, you can also, there's two notebooks. The first one is basically generating the inversion. So again, if you want to play around with SymPeg a bit, there's kind of wrappers for running the inversions. But if you go deeper in, you can get into the guts of Simpeg as well. So yeah, if you haven't used Simpeg before, I think, give it a shot. I think it's really cool. I mean, I'm still coming to grips with all the details as I was sending Dom questions late last night, but yeah, no, I think it's an amazing piece of work that all the people at UBC have done, and the community carries on. So definitely use it, and yeah, hopefully we can keep discussing this. That's all.
Cool. Well, thank you, Sean. Thanks for the talk. I think
Cheers.
Echo
Thanks,
everybody there. And yeah, we'll carry on the conversation and Swan.
Cool. Thanks.
Great. Thank you.
Yeah, thank you very much.
You're welcome. Thanks.